So thank you very much for the introduction, Bob. And also thank you so much for the organizers. It's very conference and for the opportunity. Yeah, after this really nice previous talks by Austria and the morning sessions, as well, I think it sets the stage very nicely for what I'd like to talk about. And it was advertised as a fighting session, but actually I should say that indeed, of course, we all have, there are many different points of view, but the hope is, maybe I would like to intend this more as a peace treaty towards trying to understand if we do disagree, really what precise assumptions and what aspects are different approaches, and trying to focus more on the basic assumptions where we might be different. And especially on the notion of events and causality. So I come from much more from a quantum information approach, so please forgive me if I say anything that's not accurate about the gravity or space-time side, I'm usually correct in that case. This is for the right work with really great collaborators, Lin-Ching Shen and Johan and Renato, and these two of them were here and need no introduction. We have some work in preparation, which is all very new for the past couple of weeks, but we hope to have it on the archive soon. And the talk will also touch upon a bit of previous work that I did together with which you can find during these years. So actually, the first slide is actually quite similar to this very nice motivation that Augustin previously gave. And now, I'm sure we all recognize that that the notion of events and causality is vastly different across quantum theory and general relativity, or generally relativistic and spatial temporal approaches. And at least in quantum theory, if I speak more from the informational, quantum information side of things, we've all probably seen these sort of circuit diagrams and concepts during previous talks. The notion of events and causality is closely tied to the idea of performing operations and looking at some sort of flow of information between them in some sense. And also the notion of agents or observers need to play an important role in these kind of approaches, and their ability to intervene and potentially change something. On the other hand, in relativistic approaches, the notion of events and causalities is closely tied to the idea of space and time. And often the notion of agents may not feature in such approaches. And in a sense, they are, I'm sure we all agree that to a good extent it's very important to reconcile these perspectives, and which is probably also the reason many of us are here. And on one hand, in physical experiments, we would see that these notions somehow, at least from our experience, seem to play together in some kind of compatible manner. As I put it, like spacetimes constrain what we're allowed to do with the information protocols, for instance. And on the other hand, from the fundamental side, for understanding how these two theories interact, we would also need to reconcile these notions. Of course, there are really formidable challenges, including the conceptual language and all kinds of wide differences between these views, and also the fact that if one goes more towards the quantum gravity side of things, one cannot assume that the classical background space-time anymore, in which you localize or define events. And naturally, as we've seen, there are many different approaches and theories towards trying to put these ideas together. And to a large extent, maybe this depends on the questions you're interested in asking. Here, maybe let me state the goal that we are interested in this context, which is it possible to have some kind of a more general definition of events and their localization, which would in particular recover at least certain aspects. It's not meant to be, like a unified definition, but at least it recovers certain familiar aspects of both quantum and relativistic ideas that we know of. Can we do this without assuming some kind of space-time background, and in a manner that would still permit some notion of causal relation to be meaningfully defined? And this will, of course, raise several questions, which I think we also touched upon such questions in the previous discussions. How could we define these concepts without, relative to what do we define them if we don't have this sort of notion of background space-time? Can we even speak about localization without such as spacetime, and is it possible even to reconcile these perspectives, or will they be sort of, to some extent, irreconcilable? And these are all very valid questions. And maybe I hope in the talk to present perhaps one possible operational approach which might provide an initial step forward. And the hope with that is not really to provide some kind of unified or fixed definition, but really to try to identify some structures that might be common across these different models, and try to see whether that make explicit some assumptions that we might be making when trying to define these concepts. And after this, I will try to connect it to some work we did before on trying to understand these notions of causality really in a specific regime of where you have a background in classical spacetime. Thirdly, then I will try to talk about some of the new analysis we have together with Ching and Rato on trying to analyze this quantum switch, which we heard about in previous talks, in these different classical and quantum spacetime scenarios that are presented, and see how these notions can differ. And finally, discuss some outlook and future directions. So maybe let me start by motivating some principles that we would aim to capture in this definition. And because I realize that even when we say operationalism or spatial temporalism, I think even within the operationalist camp, there are many different ideas of what we mean by operationalism and so on. So maybe just to give some context of where I'm coming from, and you feel free to question these principles in the end. So firstly, we would like to take into account what information is accessible and what operations are in principle physically possible, and try to define our notion of causality relative to that. One motivating example here comes from Maxwell-Wien paradox, which many of us know very well. And here, one could say that in a way, consistent treatment that avoids such paradox involves recognizing that this microscopic demon can, in principle, access more information and act on more degrees of freedom than a microscopic observer. We could look at it a bit more specifically relative to causality and events. I would also like to motivate the idea of taking into account what operations are in principle possible in a scenario. So, for instance, so this is sort of probably something everyone knows and very intuitive in the sense that in classical statistics and causal inference, often if the demand and price of a commodity influence each other, one would draw this sort of a cyclic graph between abstract events which correspond to some variables that influence each other. However, how we make sense of this, at least intuitively, is in some sense referring to what we can in principle do. So if we could in principle change the demand at time 1, this would only change the price of the commodity at a later time 2, which would then, if it can go and increase on the price at time 2, this would influence the demand at a later time, and so on. Another example in this regard, so this is just to illustrate that even in purely classical scenarios, this sort of an approach can give us some information on how we can reconcile these different perspectives. And the second example is the way we understand, say, the causal link between the moon and the tides. You might say that if I could go and freely change, if we had an intervention that could change the location or the size of the moon, this would change the pattern of the tides. And this doesn't mean that we have a huge agent in, whose lab contains the solar system who can actually move the moon. This is something that, in principle, we consider what is possible to change in the theory. So this is the sense in which when I use the word intervention, we do not have to always be thought of as really coming from an agent, but one could think of it more as what are the operations that are being allowed in a particular scenario we're analyzing. And this is a bit the motivation to try to bridge also another aspect of the clash that was not really that's a really nice talk. So let me outline a bit what is the basic idea behind this proposed approach. I also want to say that in most of the talk, I try to keep it a bit more also high level and conceptual, recognizing that we all come from rather different technical frameworks and backgrounds, but you can find more technical details in the paper, and I'm also very happy to observe. If anything seems vague, please feel free to ask me. So I said we don't make assumptions about the background spacetime, but obviously we have to make some assumptions. And this we will make certain operational assumptions. Firstly, we will assume that in whatever theory we are considering, we can distinguish two degrees of freedom. One is what we call the target, which are the objects that we want to study, and the other is what we call the reference. And the main purpose of this reference is that it will be used to condition operations that one performs or one considers on the target. So let me give very simple examples. So for instance, if your reference is a clock, then one could say that condition on the clock reading 3 p.m., I act on the target, which is a laser, and turn it on. And if this reference is a spin, then you could say condition on the spin being some say up, and sense of motion. And the second thing you'll assume is that one can, in principle, measure these degrees of freedom and observe distinguishable outcomes. So this is an assumption we make. Of course, defining a good measurement theory can be a big challenge in several regimes, but here we sort of, we're starting instead from the assumption that if you're given a well-defined measurement model for your theory, then what can you do with it? And I want to also really point out, because we had a very nice discussion on quantum reference frame in the morning, and it was pointed out that localization and these properties can really depend on the quantum reference frame. And I want to highlight that what we call reference degrees of freedom theories is related to, but it's a distinct notion from reference frames. And as we will see later, this also leads to a relative notion of localization, which is a bit different, but still consistent with the other notion. So we start by suggesting a definition of what elements we might want in some generalized notion of a laboratory. And of course, these are just some minimal elements. You could be like more to add on to them. So firstly, we consider some reference degrees of freedom, which, as we assumed, we can in principle measure. And we can specify such measurements by a set of operators, which correspond to the outcomes you can get of the measurement. And the set of outcomes, in principle, we consider that they decompose the space of this reference into some distinct subspaces labeled by the lambda. And this will be useful because later we'll talk about some notion of location relative to these subspaces that are being given by the reference. Secondly, we have this target, which is some other degree of freedom. And finally, we consider a set of operations that act both on the reference and target. And the idea here is that conditioned on a subspace labeled by lambda, one can apply some operation, corresponding operation on the target. And we will then consider each operation here, OA, as being an event relative to this generalized language. So here, a number of comments have to be made that actually this definition is, in a sense, quite flexible in that it encodes a lot of choices that need to be made. In fact, even given a particular experiment, it's quite possible that all of us in this room may not agree on what is the generalized lab from which we are analyzing that. And some of these choices that we would have to make, for instance, is specifying some level of detail at which we analyze the experiment. For instance, even the description of this target would depend on whether I'm analyzing this table at the level of individual atoms or I'm thinking of it as really at a macroscopic level. So this will tell us how we choose these systems RAT. And of course, also the way we divide between the reference and the target and the partition the world into these series would be a particular choice, as well as the set of operations that we consider would be interest. And I want to note that this kind of very broad idea, one could try to instantiate the different theories. And at least I could say that in particular in quantum information theory, one could make sense of these condition operations as control operations, which they coherently control on some basis or some space of the reference. And they in channels or different positive maps, unitaries, measurements. Let me take a simple example to highlight how this definition might apply. So you take a well-known example of the double slit experiment, and already in the way I've drawn this figure here, which is the familiar one, most of us, we made a choice of level of detail that we're not analyzing the atoms in the wall, for instance. And let's consider Alice to be some external classical experimenter in this scenario. And we will then consider this generalized lab analysis to include some physical reference, for instance, by asking what could she in principle access within the network. And for instance, there could now be some subspaces labeled by x1 and x2 that correspond to the equations of its. And we can observe that if Alice has access to such reference, she could independently intervene at the two slits, like independently of the photons superposition, and place some kind of phase shifting devices individually at each other. And doing so, she would notice that actually each of these individual operations has some causal influence on the interference pattern because this can shift the interference. This would specify both the set OA and how we experiment are. And finally, given these choices, you could model this as a quantum circuit where you have two operational events which really correspond to what intervention, what is somehow the locus of intervention we're allowing here. And in this case, it's associated with phi 1 and phi 2, and usually we can verify that the causal influence is something. Here, I think it's very important to point out that this very nice paper by the group here in Vienna, where they propose how not to define events, and this actually is completely consistent with that. Like what we call events here are different from what they require not to events. So in particular, these events don't correspond to asking which path the particle went through. So it's not consistent with the other view. So I would like to then motivate this property that we call measurability, relative measurability of the reference. And through a simple example again. So the idea here is that we can ask if I'm using, for instance, the wall clock as a reference. Does measuring, we would imagine that measuring this wall clock is not going to change in any way any setup that we have on the table where perhaps we are operating one photon. And this idea is captured as mentioned here, which is suggesting that we would say a reference is relatively measurable at some event OA if for whatever initial conditions are given in that scenario, not measuring the reference as compared to measuring it in the specified setup does not change what happens to the particles in the sea, which we see how the reference. And the motivation here is that it can give some idea for some notion of classicality of this reference, relative to the rest of this. And with that, we can also now try to define some condition for what we mean to localize something relative to this reference. And the idea here as well, the definition, is to consider what happens in the case where we have such an operational event, OA, and compare it to the case where we perform, we apply this in between some measurements, which both yield the outcome lambda. And if this is the case, we would say that this event is lambda localized. The intuition for this is that if we, for instance, have this operation happening within some time interval, we would expect that measuring sort of this classical wall clock before and after this operation would yield an outcome in this time interval. This is sort of the intuition that it's capturing, but it could be applied to a scenario where the reference is not necessarily made to ask whether or not relative to the reference we have some localization. Yes, so this is still a very initial approach, one could try to generalize it by having some kind of boundary condition, but that we connect it to many of these other approaches. That would be the future. So maybe moving on, I would like to
Okay. 7-8 minutes.
Okay. So I will very quickly go through the case of classical spacetimes. Because, for instance, even we can have all this sort of general abstract stuff, but we might still want to ask how can this explain what we see and maybe some of the aspects we intuitively understand in classical spacetimes. And here we would have to make some assumptions of how we instantiate the labs. So firstly, we could consider that each lab, this reference, is associated with some partially ordered set that models the background spacetime. And in particular, in this case, if there's a common spacetime for all agents, all the references for the different generalized labs would agree on that. That's an assumption of mix. And secondly, we consider here targets that will be finite dimensional points. I want to again point out that when we say space-time here, this need not be points on a manifold, as was motivated in earlier talks. Physically, we can define this in terms of physical references like rods and blocks. And maybe I will skip ahead a little bit quickly. Yes, so I would like to point out at this point, this corresponds to an earlier work we had with Renato, which is under the assumptions that you have such a common space-time, and additionally, you consider your operations to be what you can in principle do relative to this reference, then one can obtain such a theorem, which says that any quantum experiment one could perform in such a common acyclic diagonal space-time can have, at a more fine-grained level, a description that that has an acyclic ordering of the operations. And here I want to point out that when I draw this sort of diagrams, here this is really the nodes corresponding to independent quantum operations, a bit like the double slit where we do the phi 1 and phi 2 separately. I'm not going into the details here, but I'm very happy to answer more about this later. That brings us now to the quantum switch. So let's try to see how the assumptions play out there. As you've seen, this quantum switch is a scenario where you have the superposition, controlled superposition of causal order of two operations. And there's been, and this is called an indefinite causal order process. And there's been a lot of research on considering experiments or thought experiments associated with quantum switch, which we've also seen before, both this optical switch in Minkowski spacetime and the gravitational switch in this sort of superposition of semi-classical spacetimes that Victoria actually introduced in the talk. And as we've also heard, there's been a lot of discussion on this over the past decade, which relates to questions of how do we even define causality and events and so on. And so, indeed, applying this, so instantiating the assumptions we had before of the classical spacetime and really analyzing, assuming that you have agents who have access to the spacetime reference and consider what operation they can in principle do. Under these assumptions, one can recover such a fine-grained description. And this sort of involves, again, having so this, as you can see, involves, in this case, 4 independent operations, but which act on a vacuum, which models the absence of a photon as well as the photon. So when the photon goes to one path, then you have a vacuum to the other, and vice versa. And it's interesting to ask then in which situations, under which assumptions can such a description hold, and when would that, even in principle, not be possible. And I think, yes, go ahead to compare sort of these different situations. Everything that I said was just for this first case of the optical switch, but under the assumption of analyzing agents who have access to such references. As you've seen, there's also other protocols of this sort of this gravitational scenario, and the one I have here is really where if you kind of localize the mass here, and then look at now the agents being the superposition relative to the mass. And we need to connect it back to before. 2 and 3 are related within these frameworks for quantum reference frame transformations, which have been proposed in these very same works in the past. And if you specifically analyze it with the different assumptions you can have on these generalized values, in this proposed approach, we can notice that Alice's space-time reference in the first case is relatively measurable. This is like the idea of measuring the wall clock, which doesn't change what happens in the target. However, now an interesting thing happens when we consider these other two cases, because for instance here, Alice is in a superposition of being closer to the mass and further from the mass, for instance. So for this Alice, where we call it sort of the quantum switch with quantum trajectory for Alice and Bob, her spatial the relative distance is no longer, cannot be a measurable, relatively measurable reference anymore. And the same with their acceleration, because measuring this would sort of give information about the flow environment of the conversation. And I will not go into the details here, but this is sort of related, at least in this approach, to the fact that there's really different set of in-principle operations that are possible in these two scenarios. In the first case, we argued that one could independently intervene at the time 1 and time 2, relative to a wall clock, while in the second case, really Alice being a quantum trajectory fundamentally constrains her such that she cannot any longer, even in principle, intervene at the two locations. So one will get some kind of a direct sound structure in the space, even taking into account all possible operations. Again, I won't go into the details here, but one can then analyze both this relative measurability and also the idea of localization corresponding to different choices of the degrees of freedom that you might use as your reference. And this is very much consistent with what was said before. For instance, if you use the proper time, Alice's operation is localized in the proper time, as we in the scenarios. But on the other hand, in this first case, one can see that even if Alice's operation is not localized, one can kind of find ability to break it up into operations that can be localized. So with that, I'm sort of starting to get towards the end of the talk in like maybe a minute or two, that's fine? Okay, thank you very much. So I would just like to point out that in the spirit of trying to see how the different perspectives are so consistent and differ on different assumptions, I want to point out that QISS and localization are really relative to this choice of a lab that we hold. And this lab, as you said, includes a number of different assumptions on what are your references and what operations can you do. And this can be different. Given the same experiment, one could make different choices on this and therefore arrive at different conclusions on what the events are. I think I'll skip this slide, that one can use this relative measurability to identify different forms of non-localization. And indeed, in the literature, there have been very nice works by, in particular, like these time delocalized systems, by Ognian and many others, where they suggest a connection between this and indefinite causality. And this can help highlight, just in a sense, how there are different notions of non-localization in literature, which arise from different assumptions. I won't go into details here as well, but again, we're happy to discuss how the assumptions are different and understand this more. And with that, I think I will skip quite a bit and go to the conclusions, which I think already stated most of them. So maybe just leave with the open questions, as well as remain very happy to really hear your perspectives and understand if there are any further assumptions that we are making, or we need to make explicit to understand how to do together. Thanks a lot very much.
Thank you so much. And I'm really sorry. 1 minute, 1 minute.